Okay, this is what we had before for the total torque on the loop when it's rotated by a certain angle. And we found that it's the current times A times B, which is the area of the loop, times the magnetic field, times sine of the angle between R and F, times in the k-hat direction. Okay, now we want to rewrite this equation and make it in a kind of a better way or a more convenient way. And now the reason is because this problem was solved for a particular orientation of the loop with respect to the y, x, and z axis. So we have the answer in terms of k-hat. It's not very convenient to have the answer in terms of depending on the orientation of the loop in a certain coordinate frame. It would be nice to be able to get the answer for the torque in a way that's independent of the coordinate system that's being used. To do that, let's just remember that A times B is the area of the loop, and let's look at what happens when we look above from the top view. So if we look over here and look down, this is what we see when we look down. We're going to define something called the area vector. It's not the same kind of concept of area vector that we took for Gauss's law and for surfaces. It's similar in some ways, but it's not exactly the same. It's similar in the fact that the area vector is perpendicular to the loop. So the plane of the loop, you can't see it because it's in the screen, perpendicular to the screen. So imagine that you should remember this is a top view. So the loop itself is in this plane, but you can't really see the loop itself. So this area vector is perpendicular to the loop. But why did I put it this way and not that way? And that's where the convention comes in. If you use this convention, everything will work out. The convention is that if you put your fingers in the direction of the current here is coming out of the page, then you curl your fingers around the loop. Here it goes into the page. The direction of the thumb will point in the direction of the area vector. Now it's not very easy to show this in this PowerPoint slide, so you might need some help in class to see how this works better, but try to imagine that you take your fingers, put your fingers out of the page here, and then move them towards here, and then into the page here. When you do that, your thumb will point in the direction of this area vector. So that's the area vector you would take, not the other one. Now, we showed before that the torque was written in terms of this angle theta. This angle was the angle between the r vector and the f vector. We want to prove that this angle theta is actually the same as the angle between the magnetic field and the area vector that we just defined. That will make a very important part to prove the other form of the law, of the rule. So if this angle is theta, then this is 180 minus theta. And this is 90 degrees. And that means that this angle is theta minus 90 degrees, because when you add this angle plus 90 degrees, you should get 180. So if you take 90 minus 90 and minus theta plus theta, they all go and you get 180. So that's what it should be. So this angle is theta minus 90. Now if you take this angle that's theta minus 90 and you add to it 90 degrees, which will give you this whole angle, then you get 90 minus 90 plus theta, which is theta. So this angle is also theta. It's the angle between the area vector that we just defined and the magnetic field vector, which is along the y-axis. It means that if you write down the torque in this new way, writing it as I times the area vector crossed into B, if we use this formula, will this give us the correct torque vector or not? Let's look at the magnitude of this quantity. The magnitude is IAB sine theta, and we just showed that theta, which is the angle between A and B, is exactly the same as the theta that we had before. So the magnitude is exactly the same as the magnitude that we had before. What about the direction? Well, the direction of A cross B, if you put your finger in the direction of A and you curl towards B, you'll get a vector pointing in the z direction. So the direction is correct also, it's in the k direction. If the magnitude and the direction are correct, that means this gives you exactly the same vector, torque vector, as we got before. So instead of writing down the torque in terms of the way we did it before, we're going to write it as IA cross B. Now, to just make the issue of getting the area vector a bit clearer, if you imagine this loop and the current is going around this way, if you put your fingers in the direction of the motion of the current, then the thumb will point in the direction of the area vector, because if you get the perpendicular to this loop, there are two perpendiculars. One is pointing this way and one is pointing that way. Which one would you take to be the area vector? You use this right-hand rule. Put your fingers in the direction of the current and the thumb will point in the direction of the area vector. That's the rule we used to get the area vector for the loop in the previous part. So now we have that the torque is equal to IA cross B, and notice that this doesn't then refer to any particular coordinate system. When you take any loop that's oriented in space, you need to know two things. The area vector, which you can get by looking at the way the current flows in the loop and getting the area vector that's perpendicular to the loop, and then the magnetic field vector. When you know those two things, you can get the torque. You don't have to refer to any particular coordinate system. We'll define mu, I times A, we'll define that to be something called the magnetic dipole moment. We'll be able to write down the total torque as mu cross B. So this is a very compact form that doesn't refer to a particular coordinate system, and it's much simpler to use to get the torque.